Welcome to the lectures on fundamentals of MIMO wireless communications. So this is the concluding lecture of this particular course, and till now we have covered various aspects, starting from understanding the channel in quite details, which gives us which leads us to the basic assumptions which we use in derivation of the error probabilities and capacities. And then we moved on to calculating the diversity gains, whereby we learned that one could improve the error probability. Then we moved on further and looked at the capacity gains of multiple antenna systems. We have seen multiple configurations. We have also seen the effect of correlation, and we have also seen the situation when there is low SNR, or what would happen when there is high SNR, as well as we have considered the cases when the channel is random and what happens to ergodic capacity, what is outage capacity, what is the meaning, what happens when number of antennas goes to very large numbers. What we last saw is the outage capacity, or 10% or p% outage capacity is almost equal to the median value, because the distribution becomes very narrow. It doesn't spread much. So these are some of the things which we have seen, which covers the basics or fundamentals of MIMO communications. So essentially we have covered the basic tools that are required to understand or analyze any MIMO communication system, which has been the objective of this particular course. So our objective was to mainly give you a set of tools or the methods by which you could analyze MIMO systems. So given at this point whatever we have covered, you are equipped with a basic set of expressions and methods through which you can understand any advanced work on MIMO. With the help of this, you would be able to explore the further in the domain of MIMO, where there lies a lot of things to explore. For example, space-time coding, there could be transceiver architectures and multi-user MIMO configurations, and so on and so forth. So with whatever we have covered, we'd like to summarize them in this particular lecture, or move on to see how these things that we have discussed would affect a typical MIMO communication system. So till now we have seen that we can achieve spatial multiplexing and spatial diversity gain. We have seen we can achieve spatial diversity gain and spatial multiplexing gain. Right. So now suppose you are given MR, number of receive antennas, and MT, number of transmit antennas. The natural question that one can ask is what do you do with this? Would you configure it to operate in diversity mode, or would you configure it to operate in a spatial multiplexing mode? So let us see when do we do what, or what kind of combinations can be achieved. So essentially with these MR and MT transmitting receiving and transmitting antennas, one can either use it for diversity. So for diversity, we would remember various modes. You could achieve receive diversity, you could achieve transmit diversity, and there was this mode which was discussed as dominant eigen mode transmission, which would use all the antennas at the receiver and at the transmitter, and using SVD procedure it would do certain encoding to achieve diversity gain. So that uses the highest value of eigenvalue to achieve that. You could do spatial multiplexing, which could be done in two options. One is open loop. One example we gave was V-blast, and the other was closed loop. In the closed loop system, we had seen the SVD. So in this case, it is an extreme form where signals are directly sent from the transmitter to receiver. That means if there are 3 antennas, 4 antennas in this particular thing, I would send symbol 1, symbol 2, symbol 3 and symbol 4 directly into the system. Whereas in the SVD based thing, there is a pre-coding which is done before it radiates into the air. So there are extreme limits of performance. In SVD, you would require the whole channel matrix to be fed back, or the V matrix to be fed back. So other than these modes, you could actually achieve some diversity and some spatial multiplexing. So, there is a detailed theory into this diversity multiplexing trade-off, but again since this is one of the last lectures that we are doing, we will not go into the details as we have done for the diversity and for multiplexing. It is quite elaborate, and you can easily go through it now that you are trained in these diversity and multiplexing independently. But what we will show at least how can you achieve both simultaneously when it is required. So, you could achieve some aspects of diversity, some aspects of multiplexing. So, we have also seen that when there is low SNR, we have seen this in the previous lectures, the capacity C is dominated by mod of HF squared, and we have also seen that probability of error is also almost inversely proportional to HF squared. So, it is raised to the power of minus m in some form, it is not the exact form. So, when it is low, this is in general true, not necessarily for low SNR. What we said is probability of error is dominated, is probably controlled by this parameter. So, what we are seeing is that when SNR is low, this plays a vital factor. So, this gives us hints that probably at low SNR we could improve this, whereas when there is high SNR, we see that capacity is dominated by the eigenvalues or the spread of eigenvalues. We have seen this in the previous lecture. So, when we divide the multiple channels or the multiple antenna links into spatial parallel links, what we have seen is it becomes, the capacity becomes log base 2 1 plus Es by n naught, that means m times the capacity of a seesaw link. In the same manner or in the same tone, we should also say that these links have the channel strength which is similar to that of a seesaw link. So, naturally this hints that the error probability of each of the links is also similar to that of a seesaw link. So, if I have MR receive and MR empty transmit antennas, or for instance let us say we have m number of transmit and receive antennas, in that case and there is a certain value of SNR rho equals to Es by n naught, then we are left to decide what to do. Now, at this point we should note that whenever we have talked about capacity, we have when we derived or when we have actually explained intuitively what is the meaning of capacity or we used it, we actually never touched upon the error term. So, whereas if you look at the channel coding theorem, it basically tells us that we have to the capacity expression is the one which gives us the highest bits per second per hertz, which could be transmitted from the transmitter to the receiver with arbitrarily low probability of error. That means, we are talking of schemes by which your error probability almost goes to 0. So, even if your SNR is very low, it suggests that you can possibly find very large code words through the use of which you could achieve nearly 0 error probability. Whereas, in practical systems it is far from what we have just discussed. In practical systems, your code lengths are limited, you have to use the channel within finite duration of time, your channel changes with time. So, all those assumptions or all those important bases do not hold good anymore. So, you are limited because of practical constraint. So, in practical situations, we have to work with modulations and finite length code words or error correction code lengths. So, when you are using modulations, we always know that as SNR with the relationship of probability of error with SNR for AW channel is like a waterfall, whereas for Rayleigh channel it is almost like a straight, and as you increase your diversity order it becomes better. So, basically there is a primary loss in error probability when you go from AWGN to fading channel, whereas as we increase the diversity order you move more towards AWGN channel. So, this tells us that if we are already at a low SNR situation, our error probability is quite high. So, when our error probability is quite high, although we have a large number of transmit and receive antennas, we may not afford SNR upon m, which is important, because when we are doing the spatial multiplexing at each of the links we are basically giving Es by m amount of power, In case of no CSI at the transmitter, it is simply getting the channel get lambda, and when there is CSI at the transmitter and you can modify the powers, you are actually putting in an extra amount of variation. So, when we do this extra amount of power modulation, we will know that this is going to have a range. Whichever gamma is lambda is high, we put more power to that, whichever lambda is low, we put less power to that. So, that means each of the links are definitely having an SNR which is lower than the SNR of a CISO link. So, that means that each of the link is going to experience even worse probability of error. So, it from here it moves up further. So, this tells us that probably it is not a good idea to go for diversity, to go for special multiplexing mode under these conditions when SNR is so low that it does not even meet a certain threshold of error probability. So, in that case, if we use diversity combining, in that situation we might be able to bring this curve down to a situation here. If we are using MRC, it might be possible to bring it there, and this error probability point might come down here. So, what we are suggesting is if we have M antennas, our SNR is low, we have low SNR condition. So, instead of going for special multiplexing, it might be worth going for diversity. Definitely receive diversity is going to increase the array gain. If you are increasing array gain, instead of going down, you are going on the right side of the SNR axis. Further, if you are using dominant eigen mode, then you can increase the SNR even more because you are adding the average array gain at the transmitter. So, basically you are not only this line shifts bends downwards, also because of array gain you kind of shift these lines in this direction. So, overall we might be able to bring the error probability curve here from here. So, if we use diversity. So, if we are there, then we can clearly see from this not to scale diagram that when error probability was not getting satisfied, we have now moved to the situation where error probability has become much better, or the reliability of the channel has become quite good. So, whereas if we are in the high SNR regime, that means we are somewhere here, let us say we are in a 30 dB or 40 dB SNR, when SNR is here. If we distribute this SNR amongst multiple channels, suppose I get the SNRs, the average SNRs per transmit antenna at this point, so that the error probability is just satisfied, it is below this red dashed line. That means each of these parallel links would be able to sustain the error probability. So, still I mean this is just an average indication. What we actually need to do is work out these values if we are doing closed loop based MIMO schemes, or if it is open loop we have to work out these values and see what is the probability of error corresponding to the modulation that we are choosing. So, if the probability of error for the mth mode corresponding to the capital lambda m is the lowest eigenvalue, because we have said that lambda 1 is greater than lambda 2 is greater than lambda capital M. So, if this probability of error is less than some probability of error threshold, then we can choose this. If it is not true, we have to drop lambda m and have to start using lambda m minus 1. So, when we drop lambda m, we are actually dropping one of these parallel modes and we are reducing the number of modes. So, when we have lesser number of modes, we have certain amount of extra power. So, in this case, instead of ES by m, we now have ES by m minus 1. So, each of the branch are going to have extra power. So, instead of ES by m, we now have ES by m minus 1, right. So, that means the average SNR of each has increased. So, even this point has shifted here and the error probability then might be satisfied. So, we will be using lesser number of streams than would be allowed by these M antenna branches. So, basically there is a trade off which we can do. So, when we try to use this, so basically we are talking about a situation where suppose this channel is broken into U, D and V Hermitian, and we said we have to use V with S at the transmitter side in order to send this. So, this was the S tilde. So, instead of sending R streams, that means instead of S being equal to S1, S2 up to SR, where R is the rank of the matrix, we would rather send S1 to SP, where P is less than or equal to R, so that the lowest eigenmode, so that lambda P, let us say lambda P ensures that whatever is the mode of lambda P, we would have ES by let us say P number of antennas times lambda P times gamma P opt, right. This has a corresponding error probability for the pth index, which is less than or equal to probability of error threshold with some modulation order. So, if this is true, then we are going to have P transmission mode. So, if you look at this now, you are going to have S1, S2 up to SP, and this V will have length of MT. So, this will be MT cross P. So, MT cross P would mean it is MT cross P. That means, you are transmitting across all the T antennas, MT antennas, but there are P parallel streams. So, as if we can say that we are having a situation which is like this. So, there is some precoding and this is V. So, this is 1, 2 up to P. So, and this is MT cross P. So, these P streams S1 to SP are getting converted to S1 tilde to SMT tilde. So, SP streams are getting converted to MT number of symbols and then they are being sent out into the air. Similarly, at the receiver we are going to receive SP number of symbols and will decode them. So, we have P which is less than the rank of the matrix, number of spatial streams, rest of the antennas MT minus P, and on the other side MR minus P would be used for diversity gain. So, in this way we could achieve both multiplexing and diversity gain simultaneously, where the number of streams that we are sending is less than the maximum theoretical number of streams possible, so that we can support the minimum error probability. The number of streams which are less than the total number of antennas that are available. So, the excess number of antennas which are available could be used for diversity mode, and this would increase the error probability as just has been explained. So, this particular scheme requires a feedback of either H or of V. That is clear, because we will be encoding with V, right, at the transmitter. We will be encoding with V matrix at the transmitter. So, we need to talk about schemes where you do not have channel state information at the transmitter, because that would allow use of practical schemes, and that would be much beneficial than using full channel state information at the transmitter. So, one of the simplest schemes that we can draw or we can talk about would be the one where one particular example I will just take. There could be many. Suppose I have a situation which has 4 transmit and 2 receive antennas. It can have more. What we could do is we could club these two and we could club these two and say that I am going to set up 2 spatial streams, and in each of the spatial streams I could do space time coding, let us say a la Muti coding in each of them. So, in this way we achieve 2 orders of diversity at the transmitter in each of the links, and we have 2 links. So, we would improve certain amount of probability of error here, and we would achieve certain amount of spatial multiplexing. So, this is one possible way of doing it. There are many different ways of doing it, and there is a whole domain, or there is a huge amount of literature which is available which talks of space time code design, and this is a pretty rich field and there is a huge amount of literature. I would encourage you to explore this particular direction to find out how one could design code words which could provide you a trade off between multiplexing and diversity. What we have just discussed is one particular fixed scheme. So, there are many other schemes which are not necessarily fixed as shown there, but you can really move around using the different possibilities. So, we will quickly take a look at how things are done in case of LTE, which is a commercial system which uses multiple antennas. So in LTE, we are not going to talk about the OFDM. We'll simply talk about the MIMO mode. So we'll skip some of the information which may be available here. So in LTE, there are many different modes which have been proposed because of the released versions. These versions have been improving from time to time, and just 1 second. Yeah. So with these different versions or different releases as has been coming, we have with time, like release 8, then there was at one point release 9, release 10. Release 10 allows up to 8 transmit antennas. So basically it says it allows 8x8 system. So there are many versions which have been developed in LTE, that is long term evolution. So this summarizes some of the MIMO modes. There is single antenna transmission, transmit diversity, there is open loop spatial multiplexing, which we have discussed. Then there is closed loop spatial multiplexing, there is multi-user MIMO which is possible, beam forming, and so on and so forth. So all this is based on fundamentally a code book based MIMO communication. So there are code books which are used, and we are going to shortly describe some of the code books which are used in this particular system. So it allows transmit diversity. So what this particular slide tells you, we have to run quickly through this, is basically we have studied Alamuti in the time domain, right. So we have studied it in the space time block coding, whereas here it is used in the space frequency block coding. The difference here is this time that we have studied is simply replaced by frequency. So if we have studied antenna 1 at time instant 1, that gets replaced by antenna 1 subcarrier index 1 and antenna 2 and subcarrier index 2. Usually these are neighboring subcarriers or neighboring physical resource blocks. So that's the difference. Plus there is frequency switched transmit diversity. This is an additional on top of it, but fundamentally this is the Alamuti code which we have studied, which is also used in LTE. You can always use MRC at the receiver, that is always possible. So this particular slide gives you a brief overview of how it is done. So here you see clearly there is antenna 1, antenna 2. So here is subcarrier 1, subcarrier 2, but we have studied time 1 and time 2, right. So we move forward. So this is the 4 antenna based Alamuti scheme, so which is basically similar. So we'll not take a look at this. You can always take a look at these things. And then there is closed loop spatial multiplexing. So what we have studied is SVD based closed book spatial multiplexing, but here instead it is code book based spatial multiplexing. We'll explain shortly what is the meaning of code book based spatial multiplexing. So amongst the different code books, one of the simplest code books that is used is the case where there is you can see that this is the transmitted symbol, this is the code book, this is the received symbol. So code book is an identity matrix, which means that x1, the transmitted symbol, goes to the antenna as x1 and x2 goes to the antenna as x2, and you can clearly see that this is almost equivalent to the V-blast technique that we have used. So this is done in general, because if we indicate with the code book W, then for all schemes we'll be using W. In some cases we'll be using the identity matrix, which would be like indicating a V-blast. In other cases we'll be using special matrices. So the expression of writing would remain the same. So basically you would write as S times W times H is what is being transmitted, is being received along with noise. So this can be used to provide an identity matrix to indicate blast, or any other combination to provide a particular precoding. Moving forward, there is another precoding which is one of the simplest precoding as shown over here, and this is the code book's index 1. Here the code book matrix is like 1 1 1 minus 1. So in the previous case it was 1 0 0 1. So the received signal, as you can see, is x1 plus x2, and the received signal y2 is x1 minus x2. So, if I add y1 and y2, I would get x1, and if I subtract y1 from y2, what I will be getting is x of 2. So, basically y1 plus y2 is going to give x1, and y1 minus y2 is going to give x2. So, in this way also we are going to get two schemes, two signals. The advantage that we have over here is that we are basically sending the signal x1 over the different links and over x2 over the different links, so that we are able to get some better signal quality and reduce the variability of the channel. Moving forward, this particular slide gives a brief intuitive explanation that why we are going for precoding. Basically, by precoding, we are sending the signal S1 over multiple paths and S2 over multiple paths, just like similar to diversity. So, when we use this the identity matrix, that means this V blast kind of a thing, it might be that one of the channel provides you with better signal quality, the other channel is having poor signal quality. Whereas, when we send the signal across both the branches, then there is an averaging effect. This becomes a little bit worse, this becomes a little bit better, but this degradation that you are seeing over here does not affect error probability so much, whereas this improves the error probability significantly. So, basically the outage is what we would always like to minimize. So, what we see is that by virtue of averaging, we could improve the overall performance of the system. As we look forward, in these schemes, when, as we have just explained, that one has to identify the number of spatial streams, same as applying is applied over here. So, in this particular case, as we have said W, we could write it as S1, S2 up to SL, let us say, and this has to be multiplied by a matrix, right. So, definitely it needs L columns for this matrix operation to be held, right. So, basically we can have W11, W12 up to W1L, then W21 up to WM1 and WML. So, basically the number of rows that we have over here would basically mean the number of transmit antennas that we have, and the number of columns that we have would indicate the number of spatial streams that we would like to transmit. So, what we are seeing is that we could play around with this matrix and use all the transmit antennas, because you have H getting multiplied. H is H11, H12 up to H1M. So, all the transmit antennas getting multiplied. So, if there are L, if it is L is less than or equal to M, then we could reduce the number of streams. So, if my rank is a low rank channel, then I could choose only 2 streams, let us say, and I would choose only 2 columns, any 2 columns, so that my signals are spread across all the antennas, but there is only 2 signals. That means, S1 times W11 plus S2 times W12, which goes to the first antenna, W21 times S1 plus W22 times S2 goes to the second antenna, and so on. So, we are sending S1 and S2 over several multiple paths. So, basically there are 2 spatial streams, whereas these different paths provide 2 diversity gain into the system. So, for these systems to operate, the receiver needs to send to the transmitter not the full channel information, but it needs to send the rank estimate of the channel, usually through rank indicator. So, the receiver has to calculate the rank, and this is not a problem, because H is estimated at the receiver. This has to be done under any circumstance. Second thing, what the receiver should do is these code books are predefined. I'll shortly show you the code books. So, this particular example, if we take, in this particular example, we have 2 layers. So, that means 2 spatial streams or 2 data streams. So, here we can see it has 1 column and a second column, right. So, these these predefined code books are used. So, basically what we are trying to say is, in this particular expression, these W's are predefined. So, the job of the transmitter and the receiver is to now choose the best W. It does not have to use a V. It is not required to use a V matrix over here. So, in SVD case, we had y equals to u, sorry, in the SVD case we had S estimate is u Hermitian times H times V times S. This was at the transmitter side, this was at the receiver side. Whereas in and this is a function of H. So, it is connected to H. U is a function of H, right. So, this is not a problem because receiver knows H, so it can estimate, whereas this is a problem because this has to be fed to the transmitter. Now, whereas if I use W, and W is a whole set of matrices. So, what we have over here is one particular situation, whereas this particular tells us that there are whole lot of W's available. So, basically if we try to do it very quickly, we are saying that there is W1 which is a matrix, there is W2 which is a matrix, W3 which is another matrix, W4 which is another matrix. Now, these matrices are all predefined, one does not have to define W. In case of SVD, your W is basically V, and at the receiver what do you do? At the receiver it is not a problem, because one of the easiest way for a receiver is if I multiply H Hermitian and then a W Hermitian to Y. This could be one of the easiest ways of doing it. The other way I could do it is H inverse times Y times W in Hermitian, and I would ensure that W Hermitian W is equal to identity. So, in this way we have predefined matrices. So, this hints us, if we are choosing predefined matrices, the gain that we get is we do not have to calculate V, we do not have to send back V. So, if we have, let us say 16 different choices of W, all we need is 16 log 2, that means 4 bits of information to select 0 0 0 up to 1 1 1 1 to indicate different W's. So, the receiver has to find out which W is the best choice, because it can solve this also, it can solve this equation and find out which W is the best, and it has to select and send it. So, this is known as the PMI indicator or a precoding matrix indicator. So, we have a rank indicator and a precoding matrix indicator. And number 3, the third thing that we require is a CQI indicator, which is a channel quality indicator, or in other words what kind of data rate is to be supported. Because when we are choosing, let us say 2 special pipes, definitely the SNR in 2 special pipes are not going to be exactly the same. So, if there is a significant difference between them and we have to maintain the same error probability, we cannot choose the same data rate, we have to choose 2 different data rates. The higher SNR link can support higher data rate, lower SNR link can support a lower data rate. So, when you support a lower data rate, you have to choose a particular modulation and coding rate. When you support a higher data rate, you would either choose a higher modulation or a higher code rate. So, this combination gives you one particular data rate. In LTE, there are 31 different possibilities of options, which could be signaled by either 15 or even 31 different options. So, in that case, you would indicate which particular data rate to be used for which particular channel. So, it has been reduced to 3 different information instead of sending back the whole V matrix. If you had to send back the whole V matrix, you had to have, let us say m cross m elements, that would be an m squared. So, m squared elements which would be quantized by, let us say 14 bits of information. So, 14 times m squared is the overhead that is required to be signaled back to the transmitter. So, that is reduced by use of such code books in LTE. Now, details of this are available in any standard book on LTE or any reference material, and some things are also included in this particular slide, which you can read yourself and try to get a feel of what is going on in the system. So, there is also beyond this something known as cyclic delay diversity, which is also used in LTE, and beamforming is also allowed in LTE. So, in beamforming amongst different modes, one can think of that if one has knowledge about the channel at the transmitter, then what could one do? One could essentially do the SVD of the channel and find the different vectors of V, and if one uses the appropriate V vector, then what essentially one is doing is one is conditioning the channel towards the particular eigenmode. So that is very, very fundamental. So one could do that and achieve many important outcomes. So we move on, and finally I'll give you briefly that whatever we have studied using that, one can imagine the situation now that one has multiple antennas at the base station, and one could have users with single antennas or multiple antennas and so on. So the other mode which is supported in such MIMO communication system is known as multi-user MIMO mode, which itself is a pretty rich literature, and it would require a good amount of time discussing all these details. And whereas all the things that we have discussed in this course on fundamentals of MIMO communication are the basic tools which enables you to explore further into these things. I'll very briefly, very briefly touch upon this particular thing to tell you what it is all about, so that you can explore further and get into the details as per your interest. So in these schemes, if you are thinking of uplink, in this direction the users can send their own data in this direction. So if there are m number of receive antennas at the base station, and there are different users, so up to m different parallel streams can come to the base station. One can also understand that in this situation the users are usually far apart compared to the separation with the antennas. And what we have studied is that as the antenna distance becomes smaller and smaller, correlation increases between the antennas, whereas when the antenna separation increases, correlation decreases. And we have also studied the effect of correlation, that when there is more correlation in the between the antennas, two things happen. One is the diversity gain decreases and capacity gain decreases. So whereas when we have this particular situation, since antenna separation is large, it is of low probability that there will be high correlation. So all these links can be of almost independent nature. In this case, you can almost achieve m parallel links that are getting transmitted. So we could set up the equation as if there are m different symbols being sent by different users. Of course, there must be synchronization, and there is this large matrix H which gets formed, which is basically the composite of all these links. So basically between this and this there will be certain links, between this and this there will be certain links, and so on and so forth. So you could write as H11, then there could be H12 and so on and so forth from the first antenna. Similarly from the second antenna, and all of these links will form the large matrix, each one of them sending separate links, and at the receiver you receive this signal. So this expression is well known to us. If the channel is orthogonal, that means it may be possible that channels are orthogonal because users are separated by far distance. One could usually use a masked filter receiver. With a masked filter, if it is orthogonal, one could still identify the received signals. Otherwise, one could use a channel inversion if it is an invertible channel, or one could use successive interference cancellation and proceed. Whereas in the reverse direction from the base station, that means to the downlink direction, things are not that simple, and one of the very famous methods of doing it is known as dirty paper coding, through which dirty paper coding is kind of a pre-coding technique by which the interference that is experienced by different users are pre-estimated, they are pre-cancelled, and they are transmitted with appropriate weight, so that the signal that is received by user 1 is independent or is free from interference of the signal that is intended for transmission to user 2. It is not a very straightforward thing to achieve. Whereas in LTE, by virtue of having code books, it is still possible to multiplex users, so that in a fashion, for instance, one could choose different columns of these different matrices and form one new matrix which is using columns from different users in such a way that the different users data or the streams, they do not interfere with each other, and in this way, when the signal is transmitted across to the users, users would have almost interference free communication. So in this case, what I would like to point out, you can easily guess, is it is important that usually the number of users in the system is much larger than m. M is the number of transmit antennas. So if we have to choose at most m users, then we have to choose those m users which would result in an orthogonal channel, because if we can get an orthogonal channel, we have a very simple receiver to implement. Otherwise, our receiver architecture would be difficult. So if I have very large number of users in the system and I have to choose a few from them, then there is a high possibility that I can select users who would provide me a orthogonal set of channels amongst themselves. So this is a big advantage that multi-user MIMO gives us. So at least in the uplink direction, we have to find users who would provide mutually orthogonal channels. So user selection and user association is a very important task in this particular process, and followed by scheduling activity. That means if I choose a group of users who are orthogonal now, then after in the next scheduling interval, I have to find another set of users who would be mutually orthogonal. Otherwise, I would be choosing the same set of orthogonal users continuously, and the other users would be deprived of service. Whereas in the downlink direction, the problem is more to find appropriate code words which would yield mutually orthogonal signals to the receivers, because here it is assumed that the receivers are low complex receiver. That means user equipments are low complex user equipments. On the other hand, since the base station is a much more capable device, it has much more resources to operate. It can perform the signal processing algorithms which would otherwise not be possible at the user end. Whereas if it is assumed that huge amount of interference cancellation is possible at the receiver, then one could do superposition coding to achieve capacity in these particular links. So I would stop at this point with in this particular course on MIMO communications, and I hope we have been able to give you with the foundation or the basic building blocks or the elemental signal processing techniques and signal models which would allow you to explore the domain of MIMO communications further and help you in understanding deeper, better systems, more complicated systems, and able to design for the systems, as well as come up with improved version of systems which could be potentially affecting new generation communication systems. Thank you.